So picking up with part two, problem number 4, a particle moves in u of x equals 1/2 kx squared plus lambda x to the fourth. 4 parts here. Determine the equilibrium points, the stability, the frequency of small oscillations, and the first correction to the oscillation frequency due to the quartic term. So this is a nonlinear oscillator problem. So u of x equals 1/2 kx squared plus lambda x to the fourth. Our equilibrium, du dx equals kx plus 4 lambda x cubed, and that's going to equal x times the quantity k plus 4 lambda x squared set equal to 0. So x is going to equal 0, and if lambda is less than 0, x is going to equal plus or minus the square root of negative k over 4 lambda. So the stability from u double prime of x, that's going to equal k plus 12 lambda x squared. And at x equals 0, u double prime of 0 is k. So if k is greater than 0, x equals 0 is stable. And our small oscillation frequency is omega naught equals the square root of k over m. So for weak quartic and harmonicity, the equation is mx double dot plus kx plus 4 lambda x cubed. That's equal to 0. And this is a Duffing oscillator with cubic coefficient 4 lambda over m. So we could say that the frequency correction for the amplitude A is going to be omega is approximately square root of k over m bracket 1 plus 3 lambda a squared over 2k close bracket. Okay, so building on that, that's number 4. Number 5. So number 5, we just have to add a couple things here to number 5. A block begins from the rest at the top of y equals h times the quantity 1 minus x squared over a squared. And ignoring friction, we're going to determine the velocity as a function of position, the normal force, and the point where contact is lost. So this is going to be, we're going to assume that this is the point where the normal force first becomes 0. And a couple of the things we're going to assume here is assume the block slides on the outside, the top of the smooth curve. And if the chosen curve doesn't produce a finite contact loss point, then we should explain, if so. So this is a sliding block on a curved surface problem. So y equals h times the quantity 1 minus x squared over a squared. So starting from rest at x equals 0, y equals h. And the energy gives us that 1/2 mv squared plus mgy equals mgh. And 1/2 mv squared equals mg times the quantity h minus y. And h minus y, that's going to equal h minus h times the quantity 1 minus x squared over a squared, which is the same thing as hx squared over a squared. So from there, v of x equals the square root of 2gh x squared over a squared. And absolute value of x over a times square root of 2gh. So for contact loss, what we're going to do, use the normal force equation. And for a curve, y of x, that's rho equals that quantity 1 plus y prime squared raised to the 3/2 over absolute value of y double prime. And finding our derivatives here, y prime is negative 2hx over a squared, and y double prime is negative 2h divided by h squared. So we could say that the normal force vanishes when gravity alone supplies required curvature acceleration. And building on this, we could say that mg cosine phi, you could call it phi, or phi. So mg cosine, I'll say phi, equals mv squared over rho. And cosine phi equals 1 over the square root of 1 plus y prime squared. So g times 1 over the square root of 1 plus y squared. That's going to equal v squared over rho. So building on that, we could say the following for this g times 1 over this g times 1 over the square root of 1 plus y squared. That equals v squared times the absolute value of y double prime divided by 1 plus y prime to the second, that quantity raised to the 3/2. So now g times 1 plus y prime squared, that's going to equal v squared times the absolute value of y double prime. So substituting here, g times that 1 plus 4h squared x squared over a to the 4th, that equals 2gh x squared over a squared times 2h over a squared. And 1 plus 4h squared x squared over a to the 4th, that equals 4h squared x squared over a to the 4th. Now what would happen here, this would give us 1 is equal to 2, which is false. So so for this concave down parabola starting at the top, the contact loss model is singular going to the very top. So part C is undetermined. So more carefully specified geometry would be needed for this problem. And the contact loss is not a normal positive X event for the setup. So no ordinary contact loss point in the ideal model. Okay, so that's number 5. Now moving along to number 6. So number 6, we have a bead slides without friction on a vertical circular hoop rotating about its vertical diameter with angular speed capital omega. So rotating for this rotating hoop problem, we want to determine these 4 parts. Determine A, the effective potential, B, the equilibria location, C, the critical angular velocity where new equilibria appear, and D, the stability. So again, this is a rotating hoop problem. So we're going to let theta be measured from the downward vertical. The bead position has radius from rotation axis r sine theta. In the rotating frame, U sub EFF equals mg z minus 1/2 m capital omega squared times the quantity r sine theta squared. And this is with, we're going to have z equal negative r cosine theta, and U sub EFF of theta equals negative mg r cosine theta minus 1/2 m omega squared r squared sine squared theta. So our equilibria here are d U sub EFF, d theta equals mg r sine theta minus m capital omega squared r squared sine theta cosine theta, and mr sine theta times the quantity g minus capital omega squared r cosine theta equals 0. So theta equals 0 and pi, or cosine theta equals g over capital omega squared r. So from there we can say that the off-bottom equilibria exist when capital omega is greater than or equal to the square root of g over r. And our stability here, u double prime equals mg r cosine theta minus m omega squared r squared times the quantity cosine squared minus sine squared. And u double prime equals mgr minus m capital omega squared r squared. So at theta equals 0, it's stable if omega is less than square root of g over r. And we could say off-bottom equilibria are stable when they exist. And to add to this, theta equals pi, that's going to be unstable. Okay, so that's part 2. Thank you very much and have a great day.